we can now start. Welcome to the second installment of the course on learning to quantify. This is the point where we had got last time. Let me give you a brief recap of the first lesson. The first lesson we had motivated quantification or learning to quantify. We had mentioned the fact that quantification has to do with estimating class prevalence values in unlabeled data. We had motivated the fact that learning to quantify is a task different from learning to classify for a number of reasons. A task different from it and which should be taken up by learning algorithms and evaluation measures which are specific to it. And one of the reasons why the two main reasons why we want different learning algorithms is that, the main reasons are two. The fact that classifiers trained by standard methods may be biased. And the second fact is that application scenarios might be, and are often plagued by a dataset shift. So we want to develop algorithms that are robust, that are not biased, that are unbiased. So unbiased estimators of class prevalences. And we want to develop estimators which are robust to dataset shift. We have mentioned that quantification has a number of applications, and many such applications have to do with disciplines, which are more interested in aggregate data or are exclusively interested in aggregate data and are not interested in individual data. We have mentioned the social sciences, political science, market research, epidemiology, ecological modeling, and others. We have then come to discussing evaluation of quantification systems. We have mentioned that the problem of evaluation is measuring the accuracy of quantification systems. We have mentioned that measuring accuracy means measuring how much a predicted class distribution diverges from the true class distribution. And we have mentioned that there are a number of functions from mathematics called divergences, which do exactly this, measuring the discrepancy between two class distributions. We have mentioned the fact that there are some properties of divergences that we are interested in. We have mentioned that, for instance, we are not interested in the triangular property, and we are not interested in symmetry. We have instead mentioned the fact that we might be interested in relativity and impartiality. We had come to this slide in which we had essentially commented that which evaluation function is more desirable depends on the applications. For instance, the fact that the relativity measure is desired in some applications and undesired in others. Okay, so let's move on and discuss the evaluation measures which are mostly used in quantification. Actually, here I will concentrate on binary quantification, single label multi-class, and multi-label multi-class quantification. So for the moment being, I will leave out ordinal quantification. So concerning binary and single label multi-class quantification, there are many different measures which have been proposed, but actually, there are sort of three that stand out, three that are the most frequently used. In fact, 3 years ago, I set out to make a sort of a thorough analysis of all of the evaluation measures that have been proposed for quantification. And essentially, these three emerged as, in a sense, the most, certainly the most frequently used, and the first two emerge as the most satisfactory, and I will explain why. So the first one is a very simple one, absolute error. You know, what does absolute error do? Essentially, it measures for each class, the discrepancy between the prevalence value of the class as estimated by the quantifier and the true prevalence value of the class, and thus the absolute difference. So, you know, for a certain class, we predict 0.3 and its gold prevalence value is 0.2, the absolute difference is 0.1, you know. And absolute error essentially computes the average of these absolute differences across all of the classes, you know, so very simple. Relative absolute error is slightly different in the sense that it does all this, but, you know, it for each absolute difference is divided, you know, by the true prevalence of the class. This essentially means that you know, when the let's say since these are error measures, you know, the impact of this discrepancy is smaller when the prevalence, the true prevalence value of the class is higher. So this encodes the notion that in some applications, you know, a certain amount of error is much more serious if we are talking about rare classes. You know, we had made the example of rare illnesses, you know, in which if you do even a fairly small mistake, this may be serious enough. So this is relative absolute error. The third one is a completely different one. You probably know the Kullback-Leibler divergence from other areas of data science. Other areas where sometimes it's sort of the standard measure for measuring the discrepancy between distributions. Okay, so, and it is essentially motivated by information theoretic consideration. Something that we are interested in is to figure out which properties are enjoyed by which of these measures. And in this study that I'm quoting at the bottom of the slide, actually I studied which measure you know, enjoy which property. And it turns out that, of course, I mean, absolute error enjoys impartiality, so overestimation and underestimation of the same magnitude are equally penalized, while relativity does not, you know, and this is by construction, you know. And while in relative absolute error, impartiality is still holds, and also, you know, in relative absolute error, relativity is indeed enjoyed. You know, we have defined relative absolute error here in such a way that it enjoys relativity. Of more interest is the fact that of Kullback-Leibler divergence. Kullback-Leibler divergence, it turns out that it does not enjoy impartiality. So it means that you know, overestimation and underestimation are penalized differently. You know, what does this mean? Let's say the conclusion, you know, is that Kullback-Leibler divergence is not an adequate measure for evaluating quantification, for the simple reason, you know, that let's say there is no apparent reason to penalize overestimation and underestimation differently. Okay, so if let's say the true prevalence value is 0.2, and in one predictor predicts 0.1 and another predictor predicts 0.3, there is no a priori reason to say that the first predictor is better than the second, or that the second is better than the first. And which is worst of all, you know, the fact that one of the two is penalized more, let's say, is penalized more than the other, is not evident from the formula, is, let's say, well hidden in, let's say, it's not explicit in the formula, it's well hidden in how logarithms work, you know, and how this formula works. So in a sense, we don't like Kullback-Leibler divergence for evaluating quantification. Instead, you know, also based on the fact that absolute error and relative absolute error enjoy several other properties that I haven't mentioned here for brevity, you know, these two measures are to be considered the most satisfactory measures of quantification error. Which of the two is better? Of course, there is not a better one between the two, because it depends whether in a certain application you do want relativity or you don't want relativity. As we had mentioned in the previous slides, you know, in some cases relativity is desired, say the example on estimating the prevalences of illnesses, you know, and there are some cases in which relativity is undesired. The example on predicting the prevalence of no-shows on a flight-by-flight basis. Okay, so that's the basic story for binary and single-label multi-class quantification. For multi-label multi-class quantification, essentially what we have to recall is that multi-label multi-class quantification is in a sense akin, you know, to solving binary quantification for all of the different classes in the code frame, for all of the different classes in the set of classes that we consider. So we may simply use absolute error and relative absolute error in their binary version, compute it on a class-by-class basis, and average the result. So this is what in data science we call macro averaging the results of an evaluation measure. So macro averaged absolute error and macro averaged relative absolute error are the measures to use in this case. There is a word of warning, you know, is that relative absolute error and Kullback-Leibler divergence may sometimes be undefined due to the fact that the denominators might have a value of 0. So you realize this, that in this case, for instance, in relative absolute error, if the true prevalence of a certain class is 0, you know, then this formula becomes undefined. So in order to solve this, what we typically do is we smooth the prevalence values, you know, of both the true prevalence value and the estimated prevalence value by using additive smoothing, and we use the smoothed versions of the probabilities of the prevalence values in place of the original ones. Okay, so additive smoothing means essentially adding a quantity of a small quantity epsilon to the prevalence values and normalizing. Okay, and so the result is the smoothed prevalence values, you know, that are used in place of the original ones. Typically, this is the value which is used as a smoothing factor, which is half, let's say, half a count, the contribution of half an individual item. So let me come to the issue of multi-objective loss functions. Okay, so this was a proposal that was done a few years ago and has to do with the paradox of quantification that we had discussed in the introduction. So the fact that, in a sense, a classifier that makes many mistakes, but in a balanced way, such as H1, which does 1,000 true positives and 1,000 true negatives and 1,000 true positives, in terms of quantification is when, in terms of classifying count, is preferable to a classifier that does very much fewer examples, much fewer errors, okay, such as this, you know, but does them in an unbalanced way. So we had called this the paradox of quantification. And we had said that in classifying count terms, you know, I don't know, we formally we prefer H1, you know, but, you know, our intuition should makes us prefer H2, you know. So in a sense, if you build a so-called aggregative quantifier, so Alejandro will tell you about aggregative quantifiers, quantification methods, which are essentially quantification methods that rely on a classifier to take individual decisions, you know. It is difficult, in a sense, to trust a quantification methods that relies on a very inaccurate, you know, classifier. So it's difficult to trust the method if it is not based on a good enough classifier. So in order to tackle this problem, these multi-objective loss functions have been defined. What is a multi-objective loss function? It's a function that combines, in a sense, the evaluation accuracy of the accuracy of the method in terms of a certain objective with the evaluation towards another objective. So here the idea is, you know, we want the quantification method to be accurate, and this is computed by this measure. Okay, so we try to minimize the absolute difference, you know, between the false negatives and the false positives for a certain class, but we also want the classifier that underlies it to be accurate, and this is minimized by minimizing the sum of the errors, the sum of the false negatives and the false positives. So if we, in a sense, you know, minimize the product of these two factors, we go for a quantification methods that balances classification accuracy and quantification accuracy. Okay, so a quantification that may be more robust, you know, in a sense. Okay, this is a proposal that has been made several years ago. It hasn't had a huge following, I should say, but you know, it's important to note because it takes a sort of a philosophical stand towards aggregative quantification. Of course, it makes sense to use this measure as a loss function to minimize. Okay, so as a loss function, it means if you have say, if you have a quantifier that you need to train, well, this might be the measure that you optimize when you want to optimize your parameters. It doesn't make sense to use it as a measure for evaluating the final quantification accuracy, you know, because the final quantification accuracy is simply a discrepancy in the terms of the between computed prevalence values and the true prevalence value. Okay, so classification error should not be involved in this. Okay. Of course, I mean, this point is something that applies to aggregative quantifiers only. So Alejandro will tell you about the difference between aggregative quantifiers, which are quantification methods that rely on the classification of individual items as an intermediate step, and non-aggregative quantifiers. Okay, so these are methods that don't even generate predictions at the individual level. Okay, so the multi-objective loss function I've mentioned here only applies to aggregative quantifiers. The measures, you know, absolute error, relative absolute error, Kullback-Leibler divergence, the ones that I mentioned before, you know, apply to binary single label multiclass, and multi-label multiclass. Okay, so I had intentionally left out ordinal classification. So let me recall that, sorry, I had left out ordinal quantification. Let me recall that, in the classification case, ordinal classification is simply single label multi-class classification when in the case in which there is a total order on the n classes. Okay, so one example of ordinal classification is when you have to classify, say, textual comments as very negative, negative, neutral, positive, very positive. Okay, so I mean, these are 5 classes which are totally ordered, and this total order is important because mistaking, say, positive for very positive is a much less serious error than mistaking very negative for very positive. Okay, so the kind of evaluation that we should do is different. It's different in the classification case. It's also different in the quantification case. So ordinal tasks are very important in the social sciences, okay? Because in the social sciences, people tend to use ordinal scales, say ordinal set of classes, ordinal code frames, very often in order to elicit human evaluations. Okay, so in fact, when people are asked to say whether a certain product is good or not, they are provided, say, a scale of 1 star to 5 stars. Okay, so they are not typically provided, a real valued interval from 0 to 1, because it is well known that humans are not very good at providing judgments on a real value scale, but people are better at using ordinal scales for providing their judgments. Okay. So funnily enough, ordinal quantification has been found to be important also in astrophysics, where indeed, scientists use ordinal scales in order to bin energy levels, energy levels of astroparticles, which rain on the Earth from stars and other celestial bodies. What is the measure we should use here? Actually, here there are not many measures that have been proposed, and there is essentially one, which is the most frequently used measure, and it's called the Earth mover's distance. The Earth mover's distance. I'll try to give you sort of an idea on how it works. Okay, so first of all, the Earth mover's distance is a measure which has been used very frequently in other fields of data science, especially in image analysis. And the idea of the Earth mover's distance is that it basically tries to measure the minimum effort that you need to make in order to turn the predicted distribution into the true distribution. So it sort of assumes that, these, the 5 classes, okay, so these are the bars, the bars that measure the probability quantity, so the prevalence, okay. So these prevalence masses, it sort of thinks that these are piles of Earth, and that you need to move Earth, to shuffle Earth around in order to make the predicted distribution, look like the true distribution. So here, for instance, in very negative, we have this amount of predicted mass that we should move to the other classes, okay? So, for instance, we should move it here, in order to make this equal, okay? But once you move it here, also you have an over prediction. So the predicted mass is higher than the true mass, okay? So there is some amount that you should move here, and there are also amounts of prediction that you should move from here and from here to here in order to make the predicted true distribution look alike. So the idea is that the Earth mover's distance is maybe seen as measuring the minimum effort that you need to put in order to turn the predicted distribution into the true distribution. And you measure this effort by the probability mass that needs to be shuffled around between one class and the other, and the distance which is traveled by these probability masses. So if you need to take this probability mass and to bring it here, it's much different than if you need to take it from here and to move it here, you know. So this is the intuition behind the Earth mover's distance, you know, with the Earth mover's distance, which is formalized by this equation, you know, where this normalizing factor 1 divided by the cardinality of the code frame -1 is, you know, has the goal of turning the results to making all of the results fall between 0 and 1. Okay, so essentially the Earth mover's distance is maybe called the ordinal analog of absolute error. Okay, because, you know, if you assume, if you take the Earth mover's distance and you assume that all classes have the same pairwise distance, you know, okay, this defaults to absolute error. Okay, so if you assume that the distance between very negative and very positive is the same as very negative and negative, as the distance between very negative and negative, then you obtain absolute error, you know. So in this sense, we say that the Earth mover's distance is the ordinal analog of absolute error. Okay, so much for evaluation measures. Okay, so I want to now come to the notion of experimental protocols or evaluation protocols for evaluating quantification. So what is an experimental protocol? So it's something that starts from the consideration that any test set that you can use for testing the accuracy of classification can also be used as a sample for evaluating quantification. Okay, so instead of doing individual predictions of this test set, you simply evaluate the class prevalence values, you know, and you check the discrepancy between the predicted prevalence values and the true values. That's fine. Okay, there is one problem in this approach. Okay, the problem is that while for classification a set of k unlabeled data points, a set of k unlabeled data items provides indeed k tests, you know, in quantification a set of k unlabeled data points provides only one test. Okay, so if you have the traditional test set from classification, you test the discrepancy between the predicted distribution, the true distribution, and you have done one test. Okay, but you know when we test the classification systems, we normally want to test it on a data set, on a test set of many different items. Okay, and the same should be done in quantification. So how do we manage with this problem? Okay, so the idea is that we set up an experimental protocol that consists in an algorithm for extracting from a certain test set of labeled data points. You know, we extract a set of samples on which the quantifiers should be tested. You know, so we take this test set, we pick different subsets, we pick different samples, and we test the ability of our quantifier on each of these subsets. So we need to take a large enough set of subsets, we need to extract a large enough set of samples, okay, from this test set in order for our evaluation to be robust enough. Of course, I mean, it's not only important to extract many samples from our test set. It's important to extract them with a certain criterion. Okay, so a criterion that makes the resulting set U be a challenging enough test set for quantification algorithms. Okay, so an experimental protocol for quantification is a protocol that explains how to take a test set of labeled data points, let's say a test set which we normally use for classification purposes, and extract from it a set of samples on which the quantifiers should be tested. Okay, so you're probably not surprised in hearing that for different quantification tasks, say binary, multi-class, multi-label, ordinal, you need different protocols. Okay, and let's take a look at these protocols. There are two main classes of protocols that have been used in the quantification literature: the artificial prevalence protocol and the natural prevalence protocol. So let's look at them in more detail. So in the artificial prevalence protocol, what we do is we take a standard, say, data set for classification, which is split into a training set L and a test set U, L standing for labeled, U standing for unlabeled. And we extract a set of samples from U, that exhibits the highest possible diversity in terms of class distribution. Okay, so we try to extract samples that are very different between each other, that exhibit very different distributions. Okay, in such a way that this set of samples that we extract is challenging. Okay, because it's challenging for the quantifier, because the quantifier is confronted with many different class distributions to predict. Okay, so one of the pros of these protocol is that it is indeed challenging, because some samples exhibit very high amounts of prior probability shift. Okay, why is that? Okay, so suppose that our training, we have a binary task, in our training set, 30% of the items are positive, 70% of the items are negative, Well, in a sense, the artificial prevalence protocol will also extract samples, from the test set that are characterized by class distributions that are very different from the one exhibited by the training set. For instance, one sample in which the positives are not 30%, but are 90%. So 90% positives and 10% negatives, okay? Another sample with 80% positive and 20% negative, So, we generate samples that may exhibit very high amounts of prior probability shift. One of the cons of this approach, which has been criticized or mentioned, is that indeed, some of the samples that are generated might exhibit unrealistic amount of prior probability shift. And these unrealistic amounts of prior probability shift may influence the results too much. Okay. So, I mean, these are the pros and cons. Something that we will also discuss is that this protocol essentially tackles prior probability shift, okay? Because in general, you extract a set of samples that exhibit diversity in terms of class distribution. So you generate, you artificially generate prior probability shift, okay? So this is a protocol that simulates the presence of prior probability shift. It doesn't simulate the presence of other types of shift, okay, such as covariate shift. This is, in a sense, as I was mentioning at the bottom of this slide. This is, in a sense, a problem, a shortcoming of the current literature on quantification. So quantification up to now has evolved as a discipline which has mostly been concerned with prior probability shift and has largely ignored other types of dataset shift, such as covariate shift or concept shift. And indeed, we can foresee that the future research will tackle these different types of shift much more than it has been done up to now. Let me discuss the natural prevalence protocol instead, which is the other large, say, camp, in this field. The natural prevalence protocol consists in picking one or more data sets, data sets from classification that and make sure that these standard data sets represent a wide array of class prevalence values and a wide array of prior probability shift values. Okay, so in a sense, the idea here is not to simulate different amounts of prior probability shift, by the oversampling and undersampling methods that we'll discuss in the next slide, but simply pick data sets that naturally exhibit different amounts of probability shift, different amounts of class prevalence values. Okay, so what are the pros? The pros is that the experimental setting is realistic. Okay, because we have picked the prior probability shift values that occur in nature, that occur in real data. The cons is that it is very difficult to find such data sets. It is very difficult to find large enough data sets that represent a large enough array of class prevalence values, a large enough array of prior probability shift values. And because of this, the natural prevalence protocol tends to generate test sets that are much less challenging than the artificial prevalence protocol. What is the winning camp? Well, there is a clear winner, in the recent literature, and it is the artificial prevalence protocol. So the natural prevalence protocol now has almost been abandoned, due to the difficulty of finding data sets that are challenging enough, that display substantial enough amounts of prior probability shift, that display substantial enough differences in class prevalence values, and also that are sizable enough. Let us look at the artificial prevalence protocol. So this is a plot like we had seen before, So in the idea here is that you take a test set for classification. Test set may be that has a certain class prevalence. So here we are taking an example from the binary case, So the test set may have a certain class prevalence, say 90%, 90% of positives. So you extract from these test set subsamples by checking that, by controlling the prevalence values of these subsets. Okay, so for instance, you extract a subset by making sure that in this subset only 80% of the individual items are positive and 20% are negative. Here, you make sure that only 40% are positive and 60% are negative. And then you subject your quantifier, you ask the quantifier to predict the class prevalence in all of these varied scenarios. Okay, and the result of the evaluation is a plot like this. For instance, this green plot represents the ACC method. So this is a quantification method that Alejandro will tell you about. you know, and you see that the performance is really not great, you know, because, for instance, on average, you know, when the class prevalence is 0.4, you know, the discrepancy between the estimated prevalence, which is something like 0.18, and the true prevalence, which is 0.4, is sizable enough. Okay, so these colored lines represent average performance across a number of sets, and these colored bands represent variance. So the wider the band, the wider the variance. Okay, so the wider the band, the worse the method. Okay, so you might notice that when the true prevalence is very close to the training prevalence, which is represented, you know, by this blue dot, well, all of the quantification methods tend to work fairly well. But of course, I mean, the goal of a quantification method is to be able to predict class prevalence accurately, also when in the cases in which you have prior probability shift. It means in the cases in which the class prevalence is very different from the one from training. So in the more formally, the artificial prevalence protocol in the binary case essentially consists of 3 steps. Okay, so you first establish a grid of values in the 0-1 interval. Okay, so for instance, you establish 0, 0.5, 0.10, etc. You know, and the 0-1 interval is, of course, the interval in which class prevalences range. And then for each value in this grid, you extract by random sampling m different samples of k data points each, such that the prevalence value of the positive class is exactly this value. Okay, so for instance, for 0.95, you know, we extract, say, 20 samples of 1,000 data points each from our test set, such that the prevalence of the positive class in this sample is 0.95. Okay, so and if let's say if the test set exhibits a natural prevalence of, say, 0.30, this essentially means that you have to discard many negative documents, okay, and keep many positive documents. So this is what we sometimes call undersampling certain classes, you know, let's say, simulating different prevalence values by undersampling specific classes. And then you use the set of the extracted samples as the test set for evaluating the quantifiers. And this final set, how many samples has? Well, we said m samples, okay, data points each, for each value in the grid. So it's the number of values in the grid, which is 21 here, times m. So maybe you might have m equal to 100, and this will give you 2,100 different data points on which to test. Okay. Of course, I mean, this is the binary case. Using the artificial prevalence protocol in the multi-class case can be problematic. Can be problematic because if you establish a grid G like this, the number of samples that can be extracted with this method is very high, you know, because, for instance, you know, suppose you have 3 classes. Well, you know, for each of these 21 methods, okay, you can, sorry, for each of these 21 values for class 1, you pick another out of 21 values of for class B and another for class C. Of course, I mean, making sure that they sum up to 1. And the total number of samples that can be extracted is, you know, exponential in the number of classes. Okay, so in the multi-class, so you have a cubic number here, and when you have 4 class, so n is 4, etc. So you have to extract too many samples. Okay, so in this case, what we can do is that we can modify the artificial prevalence protocol in such a way that we resort to extracting samples whose distribution is extracted uniformly at random. So you pick, say, if n is equal to 5, you simply pick a random distribution from the set of all legal distribution out of 5 classes. So for instance, 0.10, 0.17, 0.13, 0.27, 0.43, and then you generate a sample, that exhibits exactly that distribution. So the idea is that the values of the class prevalence values are not constrained to fall on a grid, okay? But you simply generate a random probability distribution. You generate a probability distribution uniform at random. However, the problem is that if you want to guarantee randomness, you need to avoid naive extraction algorithms. So this is a pitfall in which ourselves had fallen in the past. And these are plots that show you that naive algorithms for extracting random distributions generate test sets which are certainly not random. So for instance, one naive algorithm is the algorithm that say pick a random, say if you have 3 classes, pick a random prevalence value for class 1, from 0, 1. Say I pick 0.6. Then, pick another, for class 2. Well, I'll pick 0.3. And for class 3, pick the remaining one, which needs to be 0.1, in order for them to sum up to 1. So you can, if you generalize this approach, to n classes, you obtain exactly this algorithm, okay? But the problem is that the number of samples, the set of samples that you have extracted in this way is certainly not random, okay? So essentially all of the probabilities in this visualization, you can see that this triangle, the triangle from which goes from here to here, is the triangle on which the class probability distributions can fall. It's the probability simplex for 3 classes, okay? So the unit 2 simplex. And you can see that by this naive algorithm, you tend to obtain, probability distributions that are concentrated in this area. Why is this so? Well, because in this algorithm, when you pick the first, the prevalence value, for the first class, you have a much bigger amount of freedom. I said I pick 0.6, but when I pick, the value for the second class, you're not allowed to pick 0.6, because the sum should not exceed 1, and so you are allowed to pick only smaller values, okay? So the very last classes, for which we pick a value are the ones that are most constrained, okay? So we don't generate something which is uniformly at random. So there are, I'll cut the story short here. There is another algorithm that equally doesn't generate a uniform enough distribution of distributions. There is the one which is currently used is called the Kramer algorithm. The Kramer algorithm is something that indeed allows you to generate a set of distributions, a set of class distributions that are indeed uniformly distributed across the probability simplex. And it simply consists of picking at random, k, or let's say a certain number of values from 0 and 1, okay? sorting them, and picking the distances between one and the successive one, and using them as the class probabilities. Okay, so this is the standard algorithm that is currently used for the APP in the multi-class case. Let's go back a bit to the natural prevalence protocol. Here is some data from one paper where this protocol was used, and it will show you some of the characteristics. Okay, so in this paper we had used essentially two different data sets called the Reuters Corpus Volume 1 V2 and OSHMED S. Let's concentrate on Reuters Corpus Volume 1. So here we had a data set of this was a data set of news, okay, of news by the Reuters company, and this is a data set of 800,000 news, which is a very large data set. It had 99 classes, So what we could do here, since it was news that lasted for it was a 1 year worth of news, a data set that covered 1 year of news, essentially what we did is we broke up the data set in 52 different weeks, We had 99 classes, which means that we had 99 binary cases, So we had 99 binary cases times 52 weeks. So it means that we had roughly 5,000 samples. 5,000 samples is a good enough, is a good enough test set, but the problem is, how many times are you lucky enough, to have a data set which is a labeled data set, which is 800,000 items times 99 classes? Not very easy, And one of the problems with this experimentation in retrospect is that this data set, Reuters Corpus Volume 1, exhibited very small amounts of data set shift. Okay, so it proved to be not challenging enough. Okay, so because all of this, the artificial prevalence protocol today is much more widely used than the natural prevalence protocol. Before I finish the part on evaluation and I leave the mic to Alejandro, I would like to mention an important fact in evaluation. So currently now there is a data challenge on quantification. Okay, so essentially something which is called a lab in the terminology of the conference which hosts it, which is the Clay conference. So it's a data challenge explicitly devoted to learning to quantify, where you can sign up your team, in order to participate. You get provided with a training set, you get provided with a test set, with an unlabeled test set, and you can showcase the ability of your quantification methods, to correctly predict the class prevalence values. So the goal of such a data challenge is essentially supporting learning to quantify research by providing a tightly controlled environment for evaluating learning to quantify systems in a comparative way. So the first edition of this data challenge ran last year in 2022, and we run again in 2024 in case you are interested in joining. In this task, essentially what we did, we used Amazon product reviews as the data, and we had different subtasks. So for instance, we had a binary subtask and a multi-class subtask. So in the binary subtasks, this was a sentiment subtask, okay, where you had to guess, whether the product review was a positive one or a negative one. And positive meant either 4 stars or 5 stars, and negative meant either 1 star or 2 stars. And of course, I mean, the goal was issuing predictions at the aggregate level. We had a raw documents subtask and a vector subtask. So for instance, one subtask in which the participants were provided vectorial representations of the documents so that you didn't have to deal with indexing text, and the subtask in which participants were instead provided with the raw documents. Okay, so they could showcase their ability to do real text quantification. And this multi-class subtask was pretty challenging because we had 28 different classes. Okay, so say in single label multi-class classification, this is challenging because for each product review, you have to guess, whether you guess the correct class 1 out of 28. You have to guess whether the review is for a book or for a home appliance or for a DVD or for whatever. Okay, and it's challenging in classification, but it's also challenging in quantification. Okay, so this finishes the part on evaluation, and maybe this is a good moment to ask questions from participants before I give the mic to Alejandro. So in case there are questions, please show up, please raise your hand, or just simply ask. Maybe if there are no questions, you can keep your questions for the end if you want, for the end of the class. And I'll stop sharing and pass the mic to Alejandro. Okay, let's check if I can do it smoothly. Okay, I should have stopped sharing. So Alejandro, you are now welcome to share yours.
Okay, can you see my slides now?
Yes, we can.
Okay. Okay, so hi everyone. Thank you for following this tutorial on quantification. Can you hear me well? I guess so.
Yes.
Okay, thank you. Okay, so I will try to offer a comprehensive overview of most important methods of supervised learning which have been proposed for quantification so far. This will consist of 2 lectures for describing methods in which we will also do some hands-on experiments. And during these hands-on activities, we will be using Python. I will show you how to implement most important quantification methods in Python. And I will also explain how to use Quantify, which is a library for estimating class prevalence, so that you can use your own dataset and problems. Okay, so I will make all the code available for you at the end of this course, so you don't have to waste any time now in setting your environment. Okay, so without any further ado, this is the link where I will make available all the material, also the slides of Fabrizio. Okay, so this is an outline of this lecture. But before getting started, let me fix some notation that which is more or less standard in the field. And okay, so we have an input space X, which is any real valued vector space with d dimensions. We have a label space Y, which with the names of the possible classes in our problem. We will use bold X to indicate any data instance. We use capital L and capital U for indicating labeled and unlabeled collections of instances. So in capital L, we have pairs of instances and labels, while in U, we only have instances. Although, you know, for experimental purposes, we might also know the true labels of the testing instances in order to, you know, to be able to evaluate our systems. Okay, so we will use sigma to denote any sample, and we use P of sigma of y to denote the true prevalence of y in the sample sigma. This is sometimes also called the prior of y. And we use caret P to indicate an estimate with a superscript M to denote that the estimate is computed by method M. We will be dealing with classifiers that we indicate with H, so standing for hypothesis, with you know, functions mapping data instances to class labels. And again, we will use caret Y to indicate the label predicted by our classifier. We will also be dealing with soft or probabilistic classifiers, which are classifiers that map data instances into posterior probabilities. And you know, this delta notation refers to the fact that posterior probability is akin to a point in a unit simplex of dimension 1 minus 1, with n the number of classes. Okay, and finally, we use capital X, Y, and caret Y to denote any random variables. Okay, so in the binary setting, we might, for simplicity, write the labels as a positive and a negative symbol. So a binary classifier is then characterized by any 4-cell contingency table in which we have counters of the number of times the true class was, for example, negative, and the classifier attributes a negative label, and so on and so forth. So we have four such counters, which are the true negatives, the false negatives, false positives, and true positives. And you know, we also have some other useful quantities as the true positive rate and the false positive rate, which are described by these two formulas, which are the fraction of correctly classified positives and the fraction of negatives that have been mistakenly classified as positives. Okay, so you have already seen this slide, I think, but a fundamental observation in quantification is that quantification is different from classification. And indeed, quantification is by now considered to be a task on its own right. So some differences, this is a brief recap. Some differences is that, you know, in classification, we deal with classifiers, which are functions mapping in input space to class labels, while in quantification, we are concerned with quantifiers, which are functions mapping samples to any point in the unit simple in the space of probability distributions. So, you know, a classifier is something that returns a class label, while a quantifier is something that returns a vector of class prevalence values. So in classification, when we speak of the error, we speak of false positives and false negatives, or more generally of misclassification rates, while in quantification, we rather speak of underestimation or overestimation. But the fundamental difference here is that in classification, we typically assume that our training and our test samples are independently and identically distributed from two distributions, while this is violated in quantification. So in quantification, we assume to be facing prior probability shift. Okay, so indeed, we perform quantification precisely because we assume there is prior probability shift. You know, this is a plot showing this distribution of class prevalence values, how these evolve over time. This is something that Fabrizio has already touched on. And so we have some different classes here. No, actually we have only one class and 4 methods here. So we can see how these prevalence values fluctuate over time in a time word span. Okay, so we should assume that there is some kind of prior probability shift, because otherwise, you know, the problem becomes simply trivial, because we can assume that the training prevalence is a good estimate for any test prevalence, and this is something which is called in literature the maximum likelihood prevalence estimator, which is, you know, is considered to be a very weak baseline for quantification endeavors. Okay, so in more detail, prior probability shift. Again, this is something that Fabrizio has already explained, but you know, it's a special case of dataset shift in which we assume that the joint distributions between training and test distributions differ because of the priors. And so we assume also that the class conditional densities do not change. So dataset shift happens in non-stationary environments or in cases in which the operating conditions are not reproducible over time. Okay, so this is a graphical example of prior probability shift in action. So we have two situations here. We have the scenario A and the scenario B, in which the only difference is the class prevalence. So in particular, in B, the number of orange dots, the orange class, is smaller. So note that a classifier that is trained to balance the number of error would be radically different if we learn this classifier in situations A or in situations B. So meaning that using a classifier obtained in A for estimating the class prevalence in B, or you know, or vice versa, would result in very poor estimates. Okay, so that's all for the introduction part. Let's take a look at some quantification methods. Okay, so quantification methods can be organized like this. So on the one side, we have the aggregative quantifiers, which require the classification of the individual items, while on the other side we have the non-aggregative methods, which do not require classification. And finally, there is another group that we call the meta quantifiers, which are quantifiers that rely on the output of other base quantifiers, be them aggregative or non-aggregative. So the aggregative quantifiers can be subdivided into those that use general purpose learners and other that use methods specifically devised for quantification. This is more or less the same. I have already told you, so I'm going to skip this one. Okay, so let's get started with the aggregative and general purpose quantifiers. Okay, so the most basic one is classify and count, which basically amounts to training a classifier on our training set L. Then using this classifier to classify all the items in a sample, and then simply counting how many or the fraction of them which have been attributed to each of the classes. So this is by far the most basic quantification method, and I will try to convince you that this is not a good quantifier. So the main reason why classifier and count is not a good quantifier is what is called the quantification paradox, which is something that Fabrizio has already explained. But in order to see why, let me consider this example in which we have, you know, a problem in which we have, you know, 100 positive versus 500 negatives, and we have these two classifiers, which is H1 and H2. So now that H1 performs much better in terms of classification because it only produces 25 error out of 600 instances. So on the other side, we have H2, which produces up to 60 errors and thus is characterized by a much lower accuracy. However, surprisingly enough, H2 performs much better in terms of quantification. So we say paradoxically, we should prefer H2 to H1 in quantification endeavors. So the problem obviously here is that the error of the H2 classifier is perfectly balanced. And, this is a consequence of the fact that classifiers are typically trained to minimize the number of false positive plus false negatives. While, a quantifier should instead try to minimize the absolute value of this difference or a proxy of this quantity, because the errors tend to compensate each other in evaluation. So of course, a perfect classifier can produce a perfect quantifier, but in real cases, we never have access to a perfect classifier whatsoever. So, okay, before going any further to other quantification methods, I will now try to convince you using Python that this is actually something that we should try to avoid. I will then share with you this notebook. So let's simply, for the moment being, let's simply run some boilerplate code, which downloads the data set, ask me permission for mounting the Google Drive, and packages this data set. You can do the same when you run these experiments in your house. So, okay, it is now packaging everything. This should take a couple of seconds. Okay, it looks like we cannot use this for some reason. Let me see if I can. Okay, no, there is some problem. Okay, I'm not gonna waste any time trying to figure out what is the problem. I will simply move forward, and I will do this in the next lecture. So let's simply go ahead with other quantification methods. Okay, so we move forward to the probabilistic classify and count, which is a method that estimates the prevalence by counting on expectations. That is by summing over soft decisions rather than summing over hard decisions. So the rationale here is that posterior probabilities contain richer information than binary decisions. Okay, so notice that probabilistic classify and count assumes that the classifier is able to return posterior probabilities. But some learners, already return posterior probabilities, like for example, logistic regression or multinomial naive Bayes. But not all methods returning posterior probabilities are well calibrated. So the notion of calibration is expressed in this equation. And, in a nutshell, we say that a classifier is well calibrated if for all examples for which the classifier predicts a posterior probability of X%, then X% of them are actually positive. So in more simple terms, for all examples for which the classifier says 80%, for example, then 80% of them were positive. Methods that do not return posterior probabilities, like, for example, support vector machines, or that are not well calibrated, like, for example, multinomial naive Bayes, can be turned into well-calibrated classifiers by applying some calibration functions. So there are many techniques for performing calibration, but likely the most popular one is the Platt method, also called Platt scaling, which consists of applying a generalized logistic function to the scores, so adjusting the parameters of a function, of a logistic function via cross-validation, so that, among all the instances for which 80% of 80% of probability of posterior probability is returned, and 80% are actually positives. Okay, so these are some examples of logistic regression for different parameters. Note that the logistic function is something mapping any real value into the interval 0, 1, so that they can be interpreted in terms of posterior probabilities. Okay, so now let's move on to adjusted classifying count. So adjusted classifying count is based on, on this formula here, which is, a pretty basic probabilistic result. So according to the law of total probability, we can obtain the sum of the system bias for each class. So that is the probability that the classifier attributes class Y to a random instance when the true class is actually J. And these values can be estimated in the training set via cross-validation. So let's go step by step. So this quantity here is actually observed and is actually something which is estimated by classify and count. Then we have the misclassification rates, or the class conditional biases. This is unknown, but we can estimate them on our training set via K4 cross-validation. While this is the true priors we want to estimate. So finally, we ended up with a system of Y linear equations with Y unknowns. So this is something that we can try to solve with standard algebra. So we can simply write this system of equations in matrix form, where, we have this vector P, CC, which stands for classify and count. This is the estimate we would obtain by using classify and count. Then we have M, which is a matrix of class conditional biases. This is what we estimate via K4 cross-validation and is computed like this. And finally, we have this P2, which is the prevalence we want to obtain, and that we can estimate simply resolving this system. This is standard regression problem. Okay, so in the binary case, this comes down to solving this equation. Here, the equation is spanned for the positive and the negative classes. And, we have this plus sign to indicate the positive class, this minus sign to indicate the negative class. And note that these two quantities here actually are the true positive rate and the false positive rate of the classifier. Of course, these true quantities are unknown, but we can estimate them in our training set. And this is a solution to this equation. So of course, this is an estimate because we are using estimates of true positive rate and false positive rate. And this method presents some problems also. So the first problem is that the estimate could ended up failing outside the range 0, 1, in which case we have to clip and rescale the the estimates, and this is something which is hardly justified from a theoretical point of view. And also, the hypothesis according to which the true positive rate and the false positive rate that we can estimate in training is a good estimate also for tests is something that can be compromised if the type of dataset shift that we are confronting is different from prior probability shift. Okay, so let's move on to another method, which is called the probabilistic adjusted classifying count. And this method simply stands to adjusted classifying count, like PCC stands to CC. So PACC uses the probabilistic estimate of PCC instead of the CRISP estimate of classifying count. And then it estimates the true positive rate and the false positive rate by summing over posterior probabilities instead of summing over CRISP decisions. So we need a probabilistic classifier here. And this results in a system of equations which is very similar to the one we have already seen for ACC. And of course, in the multi-class scenario, we can rewrite our N matrix of misclassification rates, which is now computed using the soft decisions of a probabilistic classifier, and this comes to solving this system of equations. Okay, so PCC is, among all the methods we have seen so far, is the one that tends to perform better in experimental settings, is the one that tends to deliver the best estimates of prior probability of priors of prevalence of class prevalence values. Interestingly enough, both PCC and ACC have been proposed by George Foreman, and they have been both dismissed in the same article on the grounds that, assuming that the calibration of classifiers is consistent between training and test scenarios and quantification is something which is, difficult to justify in presence of dataset shift. Okay, so we have this for classifying count approaches in which we combine adjustments with the use of probabilistic classifiers. Now we are going to move to expectation and expectation maximization for quantification, which is a method proposed by Sarens in 2002 and is a method that consists of an iterative and mutually recursive recomputation of the posteriors and the priors until convergence. So the method was originally devised for improving the posteriors probabilities, but in quantification we typically use it and take the byproducts of this method. So we run this method and we take the updated priors and we discard the updated posterior probabilities. So note that because EMQ works directly on the unlabeled documents or instances, and it computes everything during test. We could categorize EMQ as a transductive algorithm, but this is something I'm not going to cover in much detail. So, okay, let's take a look step by step about what EM actually does. So, at the beginning, EMQ first initializes the priors by picking, the priors observed in the training set. This is the first estimate of the priors in the test. And it simply initializes the posterior probabilities for the first iteration by simply running the classifier on all the test instances. And then it undertakes these two steps: the expectation step, in which the priors are updated by computing the average of the posterior probabilities in the last iteration. And then this is followed by a maximization step, in which the posterior probabilities are updated by considering this formula. Okay, so this is performed iteratively until convergence is, and the method is considered to have reached convergence when when the posteriors and the priors do not change much between two subsequent iterations. So personally enough, this is one of the methods that work best for quantification, even though it is a method that was not originally devised for quantification, and even though this method dates back to 2002. Okay, so the next method is called HDY, and let me explain this method with this nice picture from Hassan and colleagues. So the idea here is to take a look at the distributions of the posterior probabilities, which are computed independently for the positives and for the negatives examples in the training set. And then when a test sample arrives, we compute the distribution of posterior probabilities of the test. Of course, for the test, we do not know which are the true positives and the true negatives, so we cannot break down this distribution into two distributions. But the idea here is that we seek for the alpha parameter of a mixture model between the known positive and the known negative that yields a distribution of posteriors in training, which is most similar to the distribution that we have observed in the test set. And by similar, I mean the similarity computed in terms of the Hellinger distance, which is is a divergence between two probability distributions. And this is why the method is called HD, because this stands for Hellinger distance. So this method is actually one sample of a bigger family of methods, which is called the distribution matching family. We will see some others in the next slides. But the next method is called Quanet. And as you know, this was the first deep learning method proposed for quantification and was proposed in 2018. So the idea here is to produce quantification embeddings. So is to produce embeddings of sets. And these are meant to be embedded representations for the entire sample. So this embedding was constructed as a function of the posterior probabilities returned by a soft classifier, which is processed by LSTM. And the method also uses the predictions of other simpler quantification methods, like all the methods that we have seen so far. So the 4 classify and count variants and expectation maximization. Okay, so then QuantNet is trained on different samples characterized by different prevalence values, which are extracted via sampling from the training set. And the method, is trained through backpropagation in order to minimize the absolute error of the predictions. Okay, so there are other aggregative methods that I will not cover in detail in this lecture. Some are, other variants of mixture models which have been proposed by George Foreman. There are also some heuristics for deciding the classification threshold that yields, better quantification performance in an adjusted setting. There is also some work on quantification having to do with cost-sensitive classification, but I'm not going into the details here. We rather move one step forward, and we will now cover the aggregative methods which have been proposed to work with special purpose learners. So in contrast to aggregative methods based on general purpose learners, these are methods which use classifiers which have been specifically tuned for quantification. So the main problem here is that most learners can be optimized for linear or univariate losses. And this means that each test item can be evaluated independently, and the final performance, final evaluation metric, or the loss, is evaluated as an aggregation of the individual scores. But quantification methods need to be optimized for non-linear multivariate losses. And this means that the loss is not a simple average of the individual predictions for different instances, but you have to take into account the decisions made for the entire set before computing the loss. And this is something that can be obtained by using a variant of support vector machines, which is called SVM-PERF, which is something that has been proposed by Jochims. And it's a support vector machine which can be optimized for any arbitrary non-linear or multivariate measures. And there have been two different methods proposed using SVM-PERF. The first one is SVM-KLD, and the second one is SVM-Q. These are two instances of explicit loss minimization methods, in which the former is something that tries to minimize for the Kullback-Leibler divergence, while the second method is something that tries to minimize for a multi-objective measure, which is this Q measure, which is is something that is kind of harmonic mean between a classification-oriented loss and a quantification-oriented loss. Okay, so there is also some work on quantification trees, which are decision trees that use any quantification-oriented criterion for deciding how to split, the internal nodes of the trees. Some metrics that have been tested in the past, include the absolute error, or again the Kullback-Leibler divergence, or again other multi-objective functions. Okay, so let's move to the non-aggregative quantification methods, I would like to ask you if you have any questions so far before moving forward. And if otherwise, I will simply go ahead. Okay, so the non-aggregative quantification methods all depart from this observation, according to which, classification is a more general problem to quantification. So Babnik is the main inventor of supervector machines. It's, it's a very important guy in the machine learning community. So the Babnik principle states that, if you possess a restricted amount of information for solving a problem, you should try to solve this problem directly and never try to resort to a more general problem, because the information you have may be enough for solving the direct problem, but may be not enough for solving a more general one. Okay, so this indirectly suggests that using methods for directly estimating class prevalence should perform better because they try to solve a simpler quantification problem, a simpler problem. Okay, so let's take a look at one concrete example in which some researchers, which are King and Liu, try to to estimate class prevalence from verbal autopsies. So this is a setting in which we have verbal records describing the causes of death of some people, and in which we want to estimate the prevalence of the diseases, so the causes of death. So this is one of the problems that fall within the Y implies X setting, because here is the death to determine the symptoms, which ultimately are verbalized. So this can be formulated in this way. So note that here we are never trying to infer the posterior probabilities, which this is akin to performing classification via any probabilistic classifier. Okay, so one attempt for achieving this is the README system, which was proposed by Hopkins and King. And the idea is to express this equation in matrix form, in which pi are the the prevalence values we want to obtain, and in which S is a 2 to the k vector whose elements are the probabilities of each possible variate, which is a binary vector of k features, and in which we have X, which is a 2 to the k times the number of classes, which is a matrix in which the jth column has the class conditional probabilities of all the possible variates. So this poses a linear regression problem that could be resolved using standard techniques like S-square, and this is the solution to the system. And README simply estimates this pi quantity by assuming that the matrix that we can estimate in training is a good estimate for test, this X matrix. Okay, so of course the main problem of this method is that README has to deal with an exponential number of rows in the matrix. This easily becomes intractable for most problems. So the authors propose reducing the matrix, applying technique which is called buggings, which comes down to, solving different problems in which the number of features are reduced to k, and they actually use k equal to 5 in their experiments, so they perform many experiments on very small matrices that they simply average the estimations. Also by applying another technique which is called bootstrapping, which is similar to bugging, but in this case you choose a random number of rows from the matrix. So they had to implement these tricks because the problem is, of course, intractable. And yeah, there have been other attempts for solving this, the performance issues of README. Some attempts include this ISA method, which has been proposed by Theron and colleagues, and implements a series of heuristics to render the problem tractable. I am not going to enter the details here. So let's simply move forward. There is also this README 2, which is, which mainly relies on switching to word embedding representations, which are, naturally a lower dimensional than other sparse representations. They apply some heuristics to better model the discriminative power of the features. And, it's a work which contains many heuristics, and again, I think it's not terribly interesting. So let's move on to the last, I think, the last non-aggregative method that we are gonna cover in this lecture. And this is a variant of the Hellinger distance method we have seen for the aggregative quantifier. So this method is, another instance of distribution matching approaches. So here, the difference is that the Hellinger distance is directly computed on the distributions of features and not on the distributions of posterior probabilities of the classifier. So the rationale is the same. Although, in this paper from González Castro and colleagues, they propose both methods, and they show that HDY, so the aggregative variant of this method, actually perform much better in their experiments. Yeah, this is the same. This is the formulation. Okay, so before moving forward, I would like to discuss a different non-aggregative setting, and this is something that we call the symmetric approach. Okay, so it is interesting to know that quantification so far has been framed as a, as an asymmetric task. And what I mean by this is that, differently from classification, in quantification we have labels that are different in training and in test. So, to see why, note that during training, we are typically given a data set in which we have individual instances with individual labels. However, during test, a test sample is not an individual instance as in classification, So during test, the test instances are actually sets of instances, which are actually samples. And so the predictions are not at the individual level, So what we are requested to issue is predictions for the prevalence. So these are predictions at the aggregate level. So we have this asymmetry by which we have individual labels in training, but we are requested to issue aggregate labels in test. This is very weird in machine learning. I am not aware of any other task in machine learning which is asymmetric. So, an idea is to reframe the problem as a symmetric task, and we can do so by considering the training set to be composed of these elements in which we have we have samples labeled by prevalence. So note that this is not necessarily a restriction for any method, because if we have a standard data set in which we have labels for each individual item, we can simply generate via sampling a data set labeled at the aggregate level. Well, the opposite is not true. Indeed, actually, there is another area of research which is called learning from label proportions, which is exactly aimed at doing this. So, trying to infer the individual labels from samples labeled by prevalence. There are other areas of research like multi-instance learning, in which this is the case too. So, the main advantage of such a setting is that quantification would become symmetric. This is something that could be convenient, is something for which we are more used to. But this also, makes quantification methods able to solve problems in which, traditional quantification methods cannot be directly applied. Here I put some examples, like for example, post-electoral results, or demographic analysis diagnose, or problems like these uh, are typically characterized by having samples which are labeled at the aggregate level. Okay, so methods working with samples are expected to devise mechanisms for representing samples collectively. So this implies defining ways for processing variable size samples in a permutation invariant manner. So the reason is that the sample is invariant to the order in which the elements appear, and the samples can be of varying size. So any function is said to be permutation invariant with this equation holds. So when the results of the function is not altered after permuting the elements in the sample. Some examples of permutation invariant functions are the maximum, or the mean, or the median, or any other statistic computed on populations that we are used to from statistics. So, a possible architecture for any deep learning inspired model could be something like this. So we may have some feature extraction layers which are followed by any permutation invariant layer, which generates some kind of sample embedding that is then used to predict the prevalence vector out of the representation. There is one example in literature which is called HISNet Q. The Q stands for quantification. So the main idea behind HISNet is to use histograms as the permutation invariant function. Because histograms are independent of the order in which the elements are processed, because this operation, the histogram, is an operation which is natively variable size. If we compute the densities instead of the raw counts of the elements by being, and because histograms are naturally geared towards counting, so this is something that could certainly be beneficial for quantification. Okay, so the main obstacle, of course, is that histograms are not differentiable operators per se, and this is a hard constraint for training deep neural networks. So HistNetQ actually implements a trick for approximating histograms as differentiable functions by representing the bars of the histogram as a combination of two sigmoidal functions, which are, of course, differentiable. Okay, this is the last part of this lecture, which are the meta quantifiers. These are methods that simply rely on the outputs of other surrogate quantifiers for predicting K-class prevalence values. And one example is the ensemble method proposed by Pérez Gallego and colleagues in 2000, well, actually in 2017, but this improvement dates back to the 2019. So, an ensemble is typically defined as a set of base members that issue individual predictions, and then, the ensemble applies any combination rule for, for combining for issuing one single prediction out of them. So the ensembles they propose consist of training many different quantifiers in different samples of the training set. The samples may be characterized by different prevalence values, and they explored different ways for combining the predictions of the base quantification systems. So in particular, they explored the following combination rules. The first one, which simply comes down to averaging the predictions of the base member. And then they explore some selection policies for discarding some of the predictions. These policies can be static if this selection is done during training. So the static approach first estimate the performance of the base members during training and discards the weakest base member, and that simply performs the average of the remaining base members during test. They also explore two dynamic approaches, so approaches in which this selection is carried out during test. And the first approach, they explore how to select members that have been trained on samples that have a close prevalence to the prevalence that is estimated for the test sample. So the idea here is that we should rely on quantifiers that have been trained on on samples that have a prevalence which is similar to the prevalence they predict, because it's simply more reliable to think that a quantifier that has been trained on a prevalence of 50% is more likely to be right when he predicts something which is close to this prevalence, because quantifiers are typically biased towards the training prevalence. And finally, they explore another dynamic approach in which they simply discard the members whose training set is most different in terms of the Hellinger distance to the test distribution. Okay, so this is all concerning the meta quantifiers. I think this is a good point for finishing this part of the lecture. We will conclude the remaining two sections in the following lecture, and I will try to run some hands-on activities in which we will implement some of the methods we have been discussing today. In particular, we will we will implement the 4 classify and count variants and expectation maximization. I will prove that this method typically, expectation maximization typically obtain the best results if we apply some sort of, evaluation protocol for quantification. And if time allows, I will also show you how to use Quantify for, for carrying out quantification in your own dataset. Okay, is there any questions so far or any final comment? Okay, if not, thank you for following this lecture and see you next Thursday. Next Thursday. Fabrizio, do you want to say something?
No, I'm okay. So
okay.
Bye-bye all and see you next Tuesday. Thank you.
Bye.